We will start with a simple example of a concrete beam. We would normally think that the height and breadth of the concrete beam will be easy to determine, but even these values may have some variations along the length of the beam. They may not follow one of the traditional probability distribution functions, but may vary uniformly between a lower and higher value, with the prescribed value as a mean. The placement of the steel reinforcement, represented by the distance from the top of the beam to the center of the area of the reinforcement, may have a slightly higher variation, as the placement of the reinforcement bars is more difficult. Like the height and breadth, it may vary uniformly between a lower and higher value. The area of the steel reinforcement may also vary, depending on the manufacturing process, possibly following a probability distribution function close to a normal distribution. When the compressive strength of concrete, or yield strength of steel, are tested in a laboratory, the results normally have a significant variation, similar to what we saw in the experiment with the staples. The data from such tests often follows a log-normal distribution. Here are examples of yield stress measured experimentally. For the S235 steel we can see that the characteristic yield stress are determined as 235, while measurements from laboratory tests with 837, 347 and 342 specimens indicate a mean value of the yield stress of up to 310 megapascals, and a standard deviation between 17 and 31 megapascals. The mean value of yield stress is, as you can see, much higher than the specified characteristic value, and even if we take away a couple of standard deviations, we still have a value that is higher than the specified characteristic value. This is quite typical of what we find in laboratory tests, and is often assumed to be a result of the steel manufacturer making steel slightly to the safe side, rather than risking that some of the produced steel should have insufficient yield strength. Even if we perform careful tests and measurements of the mentioned parameters, and use these carefully obtained parameters in a capacity formula, we will still not be able to accurately determine the bending capacity of the concrete beam. If experiments in a laboratory is performed, it will still show some variation. All this variation have to be included in some way, when we predict a safe bending capacity of a beam. For a specific beam, this variation will be uncertainties. Even if we know the probability functions for the variation for each parameter, we don't know which value of the parameters that was drawn for this specific beam. Here are some experimental data of tubular column buckling, and the data is compared to the standardized formulas for column buckling in ISO 19902, American Institute of Steel Construction, CSA, and the Eurocode 3. We can easily see that even if we know the yield strength, and the tests are carefully performed in laboratory condition, there are still a significant variation in the experimental buckling load. This may be a result of the random variation of nature, for example in the imperfections and the residual stresses of the individual specimens, but may also be influenced by the uncertainty in measurements and reading the ultimate capacity. Further, we can see that all the standardized formulas are providing values of the buckling capacity slightly to the safe side. If we are to do calculations of the probability of the occurrence of buckling, we will need to know the bias between the standardized formula and the mean value of the experimental data, and we need to know the variation in the experimental data. Here, in the lab at the University of Stavanger, we have done tests of column buckling of tubulars with corrosion damage. On the right-hand side, we can see the measured experimental values versus the theoretical values, calculated from formulas in standards. Again, we can see that the theoretical values are slightly to the safe side, and such a result is often what we try to achieve when writing standards. In a probabilistic analysis, however, we often want to model this uncertainty rather than choosing a slightly safe value. Similar results will also be found when comparing local buckling of tubular members due to axial load, bending load, or a combination of these. Fatigue SN curves are made based on experimental work. The structural type is loaded cyclically until failure, and the cyclic stress magnitude, S, is plotted against the number of cycles, N. However, both the prediction of the cyclic stress magnitude, and the number of cycles when failure actually occurs, is a matter of uncertainty due to measuring accuracy. The figures here show a tubular joint being exposed to cyclic loading, with strain gauges used to measure the stresses at the weld. On the right-hand side, the measured stresses are shown for 8 different, but in principle identical tests. It can easily be seen that the prediction of the magnification factor for the cyclic stress, extrapolated to the weld toe, differ quite significantly in these readings. Some of this variation is likely due to random differences in each specimens, even if these are intended to be identical, but some of the variation could be due to measuring accuracy. The next problem is to plot the N in the SN curve. Failure is often defined, at least for tubular joints, as the point when the crack has grown through the wall thickness of the specimen. The problem is not so much to measure the number of cycles, but rather to figure out exactly when the crack is through the thickness. Visual examination can be quite unreliable, and a possible improvement is to define that the crack must be through thickness when the strain gauges at the starting point of the crack has lost all strain. This is more reliable, but still associated with a certain variation. In other experiments, the tubular elements have been pressurized, and the point of through thickness crack has been defined as when the pressure is released, or starting to drop. This method is intuitively quite precise, but the method is quite cumbersome in practice. If we look at the beam in a bit larger scale, the length of the beam and the weight of the beam will also be uncertain. However, normally, the greatest uncertainties in a structural problem is related to the loads. For example, the snow load on a beam will depend on the amount of snow at the given location, and as most of us know, this will vary from day to day, and is highly dependent on where in the world the structure is to be placed. What we need to do is to gather data on snow depth on the precise location, for as many years as possible, and make some statistical analysis of these values, to predict an acceptable high value. Normally, we would use the highest value, measured in each winter season, at the given location, for these statistical analysis. Wind loading will be dependent on the speed and direction of the wind at the location, which can also be established if wind measurements exists, at, or sufficiently near the location. However, in real cases, the wind load is not necessarily evenly distributed along the beam, which adds yet another element of uncertainty. In addition, the parameters in the wind load formula is uncertain. Even if we know the wind speed with precision, we cannot predict the loading with 100% accuracy. The formula in itself is an engineering simplification, with an element of uncertainty. Even if we know with some accuracy the wind speed, the snow depth, or as in this case, the wave height that is causing a loading on the structure, we are not with accuracy able to determine the loading the structure will feel. Here, the measured load divided by the predicted load is shown for many different waves on 3 different offshore jacket structures. Inaccuracy in the kinematic model we use to determine the velocity and acceleration of the water particles in the wave is a part of this variation, and the drag and mass coefficients we have chosen to use in Morrison's formula, along with variation in the amount of marine growth on the jacket legs, will also affect our ability to estimate the loading on the structure. Normally, standards will provide choices and methods that result in loads slightly to the safe side. In structural engineering courses, we are told to check that the strength of the beam is larger than the total load. Further, we have learned how to create formulas for this, based on courses on loads on structures, structural analysis and strength of materials. This is well and good, but as we now know, all the parameters in this formula is uncertain, and we have to find a way to make the decision of whether the beam is sufficiently safe, taking into account this uncertainty. You might think now that, well, I know all this, and design standards for structures gives me the values I should use. This is true for some problems, but not for all, and particularly not for problems involving aging structures, which may have serious damage, degradation and deterioration. What additional uncertainties are there for an aging structure? If the beam we have been talking about actually looks like this, what is then the uncertainties? If we don't have the original drawings and calculations, which may often be the case for an old structure, we can measure and inspect the beam to our best ability. However, the number of bars in the beam may be difficult to determine. The remaining concrete area can be measured, but will be difficult to assess with accuracy. The remaining area for the reinforcement bars, taking into account the obvious corrosive attach we saw on the last picture, will be difficult to determine. And, what strength of concrete and steel was originally used? We can look back to check what was typically used at the time the structure was originally built, but this will only give a vague indication. Maybe we can take some samples, and test these, but even that will not give us precise information. And maybe the material has lost some of its strength over the years. Hence, the uncertainty related to the strength of the concrete and steel material will be even more than for a new structure. When structures are becoming older, not only do their capacity reduce, but also the uncertainty about their capacity increases. An example of this increased uncertainty for aging structures is shown here, where to the right, the calculated moment capacity for intact concrete beams is compared to experimental measurements. Bias and variation are important measures to tell us something about the accuracy and variability of our prediction models. Bias is the average difference between the measurements and the prediction model. Variation is the spread of the data versus the model, often measured in the coefficient of variation, COV. As can be seen, there is a certain spread in the moment capacity of the new beam, but not too much. The spread is indicated by a relatively low coefficient of variation, or COV. While on the right, for a corroded beam, the COV has increased significantly and there is also a clear bias in the results. The bias and COV could possibly be reduced by a deeper understanding of the underlying physics and an improved theory. However, some of this uncertainty will be expected to be purely random. The beam may also have experienced accidents during its operation, and repairs may have been performed, which both may have changed the strength of the beam. Further, it is likely that the structure have been inspected over the years, and historic information about its condition may have been gathered. Such information may be used to reduce the uncertainty about the loading and strength of the beam. If we also have information about which maximum loads the structure has been exposed to, this will also be valuable information, and can be used to reduce the uncertainty. However, since the existing structure is being assessed, the purpose is obviously to use this structure for more years, and then we will need to look into the future degradation we have to expect. If we have some historic data of the development of degradation so far, this can possibly be predicted with some confidence, but in many cases we will have little historic data, and the predictions will be very uncertain. In addition, the design formulae for the capacity may not be applicable for degraded beams. We may have to search for data from laboratory experiments, or perform our own experiments, and develop new analytical capacity formulae. In some cases, we may use finite element method analysis successfully to predict the capacity of a degraded beam, and especially if these analysis is calibrated to laboratory experiments, this can be a good way of determining the capacity of the beam. However, there will still be uncertainties related to the actual capacity of the beam at hand, and even more so if we have less data and analysis available to determine the capacity. We could have continued this list, but I hope you by now agree that there are significant uncertainties related to structural engineering, and that we for existing structures are in a special situation. We have additional uncertainties, that makes our situation more complex, but we may also have information about the real structure, that if used correctly, can reduce the uncertainty about the structure at hand. Uncertainty is about lack of precise knowledge. So, what precisely don't we know? Physical uncertainties related to the inherent random nature, such as the variation in steel yield strength, the variability of wind loading, the variability of actual floor loading, and the physical dimensions of a structural component. We can gather more data and measurements about the structures, But also these measurements are associated with uncertainty, either due to the accuracy of the instruments, or our ability to interpret the readings from the instruments. The statistical models we choose to represent a statistical parameter will also be associated with uncertainty. Maybe we did a good choice, but maybe if we had more data, we would have done a different choice. The parameters we determine to describe the probabilistic distribution is also uncertain. The engineering models we use to describe the load and strength of a structure is normally simplified, and as we have seen in this presentation, is associated with a certain uncertainty. Further, there will be an uncertainty in if the structure will be built by the materials we described, with the geometry we defined, and particularly with the actual workmanship of the fabrication work we assumed. Gross errors is a name for the uncertainties resulting from human involvement in the design, construction, and use of structures. And finally, we may experience surprises, unknown phenomenon, or things we believe is so unlikely that it can't happen.